In this lecture we will discuss two tools that are used to help us minimize costs and to maximize profits. The first tool is called economic order quantity. It tells you how many units you should either make or buy at one time in order to minimize your inventory costs. The second tool is called constrained optimization or linear programming. It tells you which option you should take in order to minimize your costs or maximize your profits. As I mentioned, the first tool that we will discuss is economic order quantity. It applies to both ordering units and making your own inventory. It also assumes that you make or buy the same amount each time that you decide to place an order or make a production run. EOQ tells you the optimal amount of units that you should make or buy at a time. Your firm's total inventory costs consist of two things. First, it is made up of ordering costs. These are also called setup costs in the manufacturing context. In addition to ordering costs, your inventory costs also consist of carrying costs. Ordering costs consist of the following. In the case of purchasing your firm's inventory, it consists of all costs involved in placing an order. In the manufacturing context, it consists of all of the costs involved in setting up the production line that will produce your units. Carrying costs consist of all costs involved in holding inventory. It includes storage costs, insurance costs and breakage costs. Many people forget that it also includes the interest that it costs your firm to tie up the resources that are used to acquire the inventory. We will use the following variables in our discussion of inventory costs. TC will stand for the total inventory costs. P will stand for the cost to place one order for units or the setup costs for one production run. Q will stand for the quantity ordered at one time or the number of units made in one production run. Remember that these problems assume that you make or buy Q units each time you place an order or do a production run. D stands for the annual demand for your firm's units. In other words, D stands for the number of units that your firm sells in 1 year. C is the carrying cost of one of your firm's units for 1 year. Remember that inventory costs consist of ordering costs and carrying costs. We will first discuss ordering costs. Ordering costs consist of the cost to place an order, which is P multiplied by the number of orders that your firm makes in 1 year. If the problem does not give you the number of orders placed in 1 year, you can calculate it by dividing your firm's annual demand, which is D, by the number of units that you order at one time, which is Q. Since your firm's ordering costs consist of the cost of placing one order multiplied by the number of orders that your firm makes, your firm's ordering costs consist of P times D divided by Q. This graph shows how we assume your inventory levels look at any given time. Your firm orders or makes Q units, and then you sells them at a steady rate until you run out of units. At the moment that you run out of units, you then order or make Q more units, and the process starts again. Since your firm sells its units at a steady rate, then the average number of units that it has at any given time is determined by dividing Q by 2. Your firm's carrying costs consist of the carrying cost for 1 unit for a year times the number of units that your firm has on hand at any given time. On average, your firm has Q divided by 2 units on hand at any given time. So, your firm's carrying costs are C times Q divided by 2. In summary, your firm's inventory costs consist of P times D divided by Q, plus C times Q divided by 2. As you have learned in your finite mathematics class, if you want to determine the amount of a variable that you need in order to obtain the lowest possible the value of an equation, you need to take the first derivative of that equation with respect to the variable in question. You then solve for the amount of that variable that makes that derivative 0. We will now do this for Q. When you do this for the total inventory cost equation, you see that Q must be equal to the square root of 2 times P times D divided by C. This is the equation that you must remember in order to do EOQ problems. The EOQ formula tells you the amount of units that you must order or make at a time in order to minimize your firm's inventory costs. The next issue is when you should place your order or begin to make the units. This brings in the concept of lead time. Lead time is the number of days it takes for the units to arrive after the order is placed or the time it takes to complete the units after you start your production run. The reorder point is the moment when you should place your order or start your production run. It is where you have just enough units in stock to cover your sales so that your last unit in stock is sold just as the new units arrive or are completed. The reorder point is calculated by multiplying your firm's lead time by your firm's rate of usage. The rate of usage is the number of units that your firm sells in one day. For example, if your lead time is 2 days and your rate of usage is 10 units per day, then your reorder point is calculated by multiplying 2 days by 10 units per day, which is 20 units. So, you should place your order or begin your production run when you have 20 units in stock. If a problem does not give you the rate of usage, you can calculate it by dividing your firm's annual demand by your firm's number of working days in a year. Safety stock is extra inventory that your firm carries as a buffer against fluctuations in demand. For example, your firm is concerned that it may sell an extra 5 units each day. Therefore you would add an extra 5 units for each day in your lead time or 10 units to your reorder point. The extra 10 units is called your safety stock. When you have safety stock in a question, then your reorder point is the rate of usage times the lead time plus the extra safety stock that your firm requires. Assume that your firm's annual demand is 5,000 units. The annual carrying cost of 1 unit for 1 year is $10 per year. The cost to set up your machinery to do a production run is $1,000. Right now, your firm does 4 equal production runs each year. Assume that your firm has 250 working days in a year. Assume that sales occur at an even rate, and that it takes 1 day to make your units. Using the EOQ formula, you would take the square root of 2 times $1,000 times 5,000 units divided by $10. The EOQ formula tells you that your firm should make production runs consisting of 1,000 units. Since your firm has 250 working days in a year, you can divide its annual demand of 5,000 units by 250 working days to determine that your firm sells 20 units per day. Since your firm needs 1 day to complete a production run, you should start to make your units when your inventory level drops to 20 units. If your firm wants safety stock, then you would add the amount of the safety stock to the 20 units in order to get the reorder point. The problem said that your firm makes 4 equal production runs in a year. If you divide 4 into your firm's annual demand of 5,000 units, you see that your firm makes 1,250 units at a time. Your firm's current inventory costs when it makes production runs of 1,250 units are $1,000 times 5,000 units divided by 1,250 units plus 1,250 units times $10 divided by 2. This gives you an annual inventory cost of $10,250. If your firm had made units in 1,000 unit production runs, its annual inventory costs would be calculated by multiplying $1,000 times 5,000 units divided by 1,000 units plus 1,000 units times $10 divided by 2. This gives you an annual inventory cost of $10,000. Thus, you see that your firm can save $250 by making units in production runs of 1,000 units rather than production runs of 1,250 units. Our next topic is constrained optimization. It is also called linear programming. In these problems your firm either wants to minimize its costs or maximize its profits or contribution margin. If all you wanted to do is to maximize your profits or contribution margin, you would make an infinite number of units and you would have infinite profits. Of course, you can't make an infinite number of units because you have capacity limits. Similarly, if all you wanted to do is to minimize your costs, you could go out of business. This would give you 0 costs. In reality, you want to minimize your costs while achieving certain production goals. Constrained optimization covers the situation when you want to minimize costs while achieving specified production goals, or if you want to maximize your profits within specified capacity limits. We will talk about solving a constrained optimization problem using the graphical approach. With the graphical approach, the first thing that you must do is to state your goal, which is called the objective function. Your goal is to maximize your profits or your contribution margin, or it is to minimize your costs. You write this as a mathematical formula, and the variables in the formula are the variables that you can change in order to minimize your costs or maximize your profits or contribution margin. For example, assume that your firm makes two types of bolts, bolt A and bolt B. Bolt A produces a contribution margin of 10 cents for each unit sold. Bolt B produces a contribution margin for each unit sold. Your firm wants to know how many of each type of bolt it should produce and sell. So, you would write your objective function as max 10 cents times A plus 12 cents times B, when A represents the number of A bolts that your firm makes and B represents the number of B bolts that your firm produces. As we mentioned earlier, without any constraints, your firm would make an infinite number of both types of bolts and have infinite profits. So, we have to add your firm's capacity limits to the problem. Assume that both of the bolts must pass through 3 machines and the time that each machine is available to produce the bolts is limited. Assume that machine 1 needs 1/10 of a minute to produce an A bolt and 1/10 of a minute to produce a B bolt. Assume that machine 2 needs 1/10 of a minute to produce an A bolt and 4/10 of a minute to produce a B bolt. Assume that machine 3 needs 1/10 of a minute to produce an A bolt and 1/2 of a minute to produce a B bolt. Also assume that the time on machine 1 is limited to 240 minutes in a day, that the time on machine 2 is limited to 720 minutes in a day, and the time on machine 3 is limited to 160 minutes in a day. We now add these constraints to our objective function so that our problem reads as follows. We want to maximize 10 cents times the number of A bolts that we sell plus 12 cents times the number of B bolts that we sell, subject to the following constraints. The constraint regarding machine 1 states that the time that we use machine 1 cannot exceed 240 minutes. You say this mathematically by writing 1/10 of a minute times the number of A bolts that we sell plus 1/10 times the number of B bolts that we sell must be less than or equal to 240 minutes. The constraint regarding machine 2 states that the time that we use machine 1 cannot exceed 720 minutes. You say this mathematically by writing 1/10 of a minute times the number of A bolts that we sell plus 4/10 times the number of B bolts that we sell must be less than or equal to 720 minutes. The constraint regarding machine 3 states that the time that we use machine 1 cannot exceed 160 minutes. You say this mathematically by writing 1/10 of a minute times the number of A bolts that we sell plus 1/2 times the number of B bolts that we sell must be less than or equal to 160 minutes. You must also state that we cannot sell a negative number of A bolts and B bolts. This may be obvious, but it is still one of your constraints. If you ask a computer to solve this problem, the computer may tell you to produce a negative number of one of the bolts being sold unless you put in this. The next part of the graphical approach to solving a constrained optimization problem is to graph the feasible region. This is the area that includes all of the possible solutions that meet all of the constraints. Your graph of the feasible region consists of a Cartesian axis made up of your two variables, which are bolt A and bolt B. In this graph, you see the feasible region that satisfies the non-negative constraint for the number of A and B bolts sold. It consists of the top right quadrant of our Cartesian axis. We now want to add the other constraints to the graph. The other constraints consist of inequalities. An inequality consists of a line and 1/2 of the plane divided by that line. In order to graph our inequalities, we want to first come up with the line that divides the plane. To do this, think of the inequality as an equality, and graph that line, then choose the side of the line that satisfies the inequality. For example, let's graph the constraint dealing with the limited time on machine 1. This is 1/10 times A plus 1/10 times B is less than or equal to 240. First write this as an equality, which is 1/10 times A plus 1/10 times B is equal to 240. Now, we have to graph that line. In order to graph a line, you need to identify 2 points that lie on that line and then draw a line that runs through both points. The easiest 2 points to identify are the points where the line crosses each Cartesian axis. This is because, when the line crosses the A-bolt axis, the number of B-bolts must be 0. Similarly, when the line crosses the B-bolt axis, the number of A-bolts must be 0. It is very easy to multiply numbers by 0. So, we will identify where our machine 1 line crosses the A-bolt axis. The equation of the line is 1/10 times A plus 1/10 times B is equal to 240. We now substitute 0 for B because the number of B-bolts is 0 when your line crosses the A-bolt axis. This leaves you with 1/10 times A plus 1/10 times 0 is equal to 240. You now move the 1/10 to the other side of the equation. You now see that the number of A-bolts is 240 divided by 1/10, which is 2400 units. So, we know that the machine 1 constraint line crosses the A-bolt axis at 2400. We now want to know where the machine 1 constraint line crosses the B-bolt axis. So we start with 1/10 times A plus 1/10 times B is equal to 240, and we substitute 0 for A because the number of A-bolts is 0 when the line crosses the B-bolt axis. When you solve for the number of B-bolts you get 2400 units. So, we know that the machine 1 constraint line crosses the B-bolt axis at 0,2400. Now that you know 2 points on the line, you can graph the machine 1 constraint line. We now need to know which side of the line to include in the inequality. The easiest way to determine which side of the line to include in our graph of the inequality is to pick a point on either side of the line and test it to see if it satisfies the inequality. If it does, then the inequality includes the side of the line where the point is located. If the point does not satisfy the inequality, then the other side of the line satisfies the inequality. The easiest point to test is the origin because you again get to multiply by 0. So, we will plug 0,0 into our inequality. We want to know if 1/10 times A plus 1/10 times B is less than 240 when the number of A and B bolts are both 0. 1/10 times 0 plus 1/10 times 0 is equal to 0, which is less than 240 minutes. So, we know that the side of the line that contains the origin satisfies the machine 1 constraint. This graph shows the shaded area that satisfies the non-negative constraint and the machine 1 constraint. We now want to graph the machine 2 constraint. First we turn the constraint into an equality, which reads 1/10 times A plus 4/10 times B is equal to 720. Next we make B equal to 0 to determine where the line crosses the A-bolt axis. When we solve for A, we see that line crosses the A-bolt axis at 7200,0. We now use the same process to determine that the machine 2 constraint line crosses the B axis at 0,1600. When we test the origin, we see that the machine 2 inequality includes the side that contains the origin. We now add the machine 2 constraint to our feasible region graph. The shaded area represents the area that satisfies the machine 1 constraint, the machine 2 constraint, and the non-negative constraint. We now want to graph the machine 3 constraint. First we turn the constraint into an equality, which reads 1/10 times A plus 1/2 times B is equal to 160. Next we make B equal to 0 to determine where the line crosses the A-bolt axis. When we solve for A, we see that line crosses the A-bolt axis at 1600,0. We now use the same process to determine that the machine 3 constraint line crosses the B-axis at 0,320. When we test the origin, we see that the machine 3 inequality includes the side that contains the origin. We now add the machine 3 constraint to our feasible region graph. The shaded area represents the area that satisfies the machine 1 constraint, the machine 2 constraint, the machine 3 constraint and the non-negative constraint. Note that the shaded area does not touch the machine 1 or machine 2 constraint lines. This tells you that these constraints are non-binding. In other words, the optimal result that we are determining would be the same even if there were no time limits on machines 1 and 2. Now that you have the feasible region that satisfies all of the constraints, you need to identify the points that will give you the minimum cost or the maximum profits or contribution margin. The corner points of the feasible region give you these minimum and maximum points. So, you need to identify the corner points of the feasible region. In this problem, the corner points of the feasible region are 1600, 0, 0,320, and the origin. You next plug these values into the objective function and you see which corner point gives you the largest contribution margin. That is your solution. In this problem you get the maximum contribution margin from producing 1600 of the A bolts and none of the B bolts. The end.